Okay, so you already know that homework 12, you've got until 11:59 on Friday to submit that assignment. And then our final exam is going to be the following Friday. It's from 12:45 p.m. to 2:45 p.m. And as with our previous exams, the PDF file will become available on Blackboard right at 12:45 p.m. And so you can print out the exam and work on that paper, or if you like, you can just leave the test on the screen and use a blank piece of paper. The exam is comprehensive, and so it may include questions from any point during the semester, including closed conduit flow up through the open channel flow that we're doing now. But there will be added emphasis on the more recent material that you haven't yet been examined on. And so what that means is that there may be disproportionately more questions and more point value coming from the material that started with lecture 32. So it was in lecture 32 that we started talking about the momentum depth function, hydraulic jump, underflow gates, gradually varying flow, and so on. And the conditions of the exam are the same as the first two, where you are permitted to use your homework assignments, your previous examples, your notes, your textbook. But what you shouldn't do is access any web resources, including videos, and you shouldn't communicate with other people during the test. And what you submit should be your work. It shouldn't be anybody else's work. It should just be what you managed to figure out. Okay, so today we're going to continue talking about methods to calculate the water surface profile. And before we do that, are there any questions related to the announcements? You know, actually, by the way, let's take a moment, because I've been getting these reminder emails, and I think that you probably have as well, about course evaluations. And I don't get to see the course evaluations until after the semester is over and after the grades are posted and all that. So I don't see any of the remarks, but what I was able to notice is that very few people have done the course evaluations yet. And student feedback is important to me. I take seriously the suggestions you've got and the concerns you have, and you know, maybe now's a bad time for me to ask for your feedback, since everybody's kind of burned out with the semester and feeling crushed with all the projects and assignments and stuff. But in the past, I've been really fortunate to get meaningful, constructive feedback from students in the past, and they've offered a lot of suggestions that I've incorporated into my classes. And so I really am sincerely interested in always trying to do a little bit better than I did the semester before that. So I'm interested to know what you like, if there are certain things that I should continue doing that you think are valuable, if there are things that you didn't think were particularly important. And one issue in particular that's always on my mind is getting the right balance between problem solving and theory. And I know that there are some professors who maybe would spend the entire 50 minutes talking about the theory and the fundamentals, and not spend any time on problem solving. And so I'm always a little bit uncertain whether I've struck the right balance between giving you a preview of hands-on calculations and more theory. Let me do this. I'm going to paste the link to our course evaluations there into the chat window. And let's see, copy link location. So I think I can paste the link, and then you can click on it. And if that doesn't work, so it's there now in the chat box. I don't care if you do any of the other classes. I mean, it's good if you do, but it's the evaluation for 331 that I'm most interested to have. So I'm going to pause for a second, stop talking, give you a chance to fill out these surveys, and so probably at 1:10, so I'll give you roughly 5 minutes to go through that feedback. And all right. All right, so we've talked about the announcements, and we're going to continue talking about water surface profiles today. And what we were talking about last time was the direct step method. And what we did with the direct step method was we were trying to predict the length of the backwater curve. Remember that the unknown was a distance. And what we were trying to solve was how far was it, in the example we did, between segments of known depth. and we knew what the depth would be upstream of an obstruction. And so here was a broad-crested weir, and you were given that the depth immediately upstream of that broad-crested weir was 3.8 meters. And what we wanted to know overall was how far upstream do we need to go to where we're going to start to see the normal depth again, where there isn't any sort of pooling occurring. And what we learned with the direct step method from last time is that if we divide the section into segments where the vertical deflection between depths is no more than 0.5 meters, that we can add up those different pieces, and we're essentially approximating a curve with a series of straight lines. And so from 7 to 6, that was a straight line. From 6 to 5, a straight line. And so we were trying to kind of integrate the change in depths with this direct step method that was in that spreadsheet approach that we used last time. And numerically what we were doing was we were at the midpoint between sections, asking ourselves how much energy has changed as we're working upstream, and then we're using that change in energy to estimate the average slope of the energy grade line. And then with that average slope of the energy grade line and the change in specific energy between the two segments, we calculated the length of the backwater segment between those two depths. And so, you know, how did we know which depths to use for, like, for example, Y6? It could be any depth. You can use the DL formula for any depth, and it's just that we divided it up into equal increments of vertical deflection. And so we knew that in the end we wanted our last segment to be the normal depth, so we just kind of split the depths up that way. But it didn't necessarily have to. It could have been, I could have said, like, I want to know how far is it from where the depth is 3.8 to where it's 3.7. And then I'd want to know how far is it to 3.5 and 3.3. You know, we could have picked whatever depths we wanted and calculated the length that way. Anyhow, this method has some limitations. And most notably, this method is limited to sections that have the same geometric shape. So it's not readily applicable to natural channels, where in the case of a natural channel you may have it really wide in one section and relatively less wide in another, or it could be transitioning from a rectangular profile to trapezoidal. And so this direct step method doesn't quite work for any case where the prismatic channel is changing geometry. So we need a different approach for that. And the different approach we're going to use is the standard step method. So the direct step method from last time only is for a cross-sectional shape that's not changing, and this standard step method works regardless of whether the shape is changing. And so it's the standard step method that is kind of the genius running in the background on programs like HEC-RAS. And I think most likely some of you work over at the Army Corps. I mean, that's generally the case, that some of our students are employed part-time at the Army Corps of Engineers. And so if you are, most likely you've heard of the software called HEC-RAS, and if not, I'll tell you briefly. It's a program that calculates the depth of the water for a certain flow rate. And so you build a channel, you kind of tell it the geometry of the river, like what do the sides look like, what does the bottom look like, and then you put water through that channel. And it uses the standard step method to predict what will be the flow depth at different cross sections in that channel. So we're going to look at the theory behind the standard step method before we get into the particulars and the calculation process that's in that spreadsheet template that I emailed you earlier today. And the first thing I want to point out is that so far this semester we've always said that location 1 was the upstream location and location 2 was downstream. Like when we were doing pipe flow calculations and we applied the energy equation, or in open channel flow when we were doing specific energy analysis, our previous convention has always been that 1 was upstream and 2 was downstream. But that kind of gets turned a little bit on its head with the standard step method. So instead, our new convention for the standard step method is we're going to use the number 1 at the location where we know the depth. And then location 2 is where we're going to be trying to calculate the depth. And so we have this red alert here just to draw your attention to the fact that there's a slight change in what we mean by 1 and 2. So for example, in this illustration, you can see here's an open channel flow. This is a cross-sectional view, and so we have the bottom of the channel. We've got the water surface. Here's the energy grade line, and then this upper dashed line is just horizontal. And so here's our horizontal datum at the bottom. Here's horizontal up above the total energy line. And so location 1 is a spot where we know the depth, and location 2 would be the spot where we're trying to calculate the depth. And what we generally will do is if we have subcritical conditions, then location 1 would be a downstream location, and we would work upstream towards 2. So for subcritical conditions, you'd start where you know the depth and work upstream, but in supercritical conditions, it's the reverse of that. You would begin with a known depth at your upstream location and then work downstream towards location 2 being the unknown depth. Okay, so with that little wrinkle in the back of your mind, this is just an energy balance like it's been so many times before. We're just looking at these two locations and we're adding up all the different places that the energy can be. And so there's no surprises here. For instance, at location 1, we've got the elevation from the datum to the bottom of the channel. So maybe that would be from sea level. You know, sea level is a pretty common datum. And so you'd know the bottom of your river is some distance above sea level. And then Y1 would simply be the depth of the water above the channel bottom. And you can see here, it's defining the water surface as the elevation of the water above the datum. And so in other words, WS, water surface, is the sum of just the Z1 component and the Y1 component together. Okay, so WS is the elevation of the channel above the datum and then also the depth of the flow. And then of course on top of that we've got our velocity head, and then on the downstream end, so this is on the right side, so it's downstream. On the downstream end above the energy grade line is some head loss. And now remember, this is non-uniform flow. So in non-uniform flow, the total energy line is not parallel to the water surface, and that is not parallel to the bottom of the channel. So just keep in mind, we wouldn't be applying either the direct step method or the standard step method if conditions were steady and uniform. If it was steady uniform flow, we just use Manning's equation. But here we have non-uniform flow, so we're trying to calculate what is the depth by doing a different analysis. We'll be essentially applying a balance of specific energy, but we have to do things a little bit differently because the channel geometry might be changing. So let's talk about how we handle that. Now, the method is we know the depth at 1. We don't know the depth at 2, so we're going to guess. And remember, we did this in a lot of previous numerical methods where we didn't know exactly what some value was, like a flow rate, for example, or a head. But just to get the ball rolling, it's like an iterative process, and so you have to start with a guess and then you'll improve on the guess. Remember how we've done that before? Well, we're doing it again. So we don't know exactly how deep the water is here at location 2, so we'll just start with a guess. We'll assume some depth, and you can have a pretty good guess if you look at the water surface profile. You know, for example, here at location 1, you know the given depth, and you have enough information that you could calculate the critical depth and the normal depth. And so you could, if it's an M1 profile, then that would tell you that the water is getting less deep as you move upstream. Or if it's an M2 profile, then that would tell you it's going to be deeper in the upstream direction. And so your guess for how deep is the water at this unknown location maybe will be informed by how you previously have classified the water surface profile. But you just assume some depth, and so therefore, if you know Y2, if you guess Y2, then you can therefore have a guess value of the water surface. So you assume a water surface elevation, and then based on that assumption, or based on that initial guess, you would calculate how much head loss is there between location 1 and location 2. And in this case, the flow is going from 2 towards 1, and so our head loss is going to be the energy that there was at 2 minus the energy that there was at 1. So the upstream minus the downstream location. So that would be our observed head loss, which is based off of a guess. And now you'd calculate the head loss that there must be based on the change in velocity head between the two locations. And we'll see that there's a coefficient that ties into that. It's kind of like how there's a coefficient when you have a channel expanding or contracting. But the calculated head loss is the slope of the energy grade line at the midpoint. So S sub F with this bar over the top of it just means at the midpoint, what is the slope of the energy grade line? So the slope of the energy grade line multiplied by the length will give you a calculated head loss. And the calculated head loss, you can see, is based on, you want to know at 1 and at 2 what is the slope of the energy grade line based on Manning's equation, and then you find it at the midpoint. So this is similar to what we did in direct step. Then you compare observed and calculated head loss. Now it's likely not going to be exactly the same, and if it's not, then that means you have to come up with an improved guess of what is the water surface elevation. And we're going to call that the calculated water surface elevation. So you base the new estimated water surface depth on the previous velocity head and the calculated water surface, which is based on the calculated head loss. And so you put it into this formula. So you remember here at location 2, we don't know what the depth is, but since we don't know the depth, we also don't know what's the velocity head. So the velocity head is essentially a guess as well. So we're going to go through this cycle of making a guess, making a small correction, and improving on the guess in subsequent iterations. So this updated water surface that you should use in the next cycle of your iterations is going to be your initial assumed value for the water surface plus the calculated divided by 2. So rather than going all the way to this calculated water surface depth, it will allow the solution to converge if you instead take a more incremental approach and split the difference between your previous guess and this updated calculated version divided by 2. And I think you'll see why that's necessary as we go through the spreadsheet itself. So we will just do this as many times as required until there is convergence, meaning until the observed and the calculated head losses are the same. And when they are the same, then we know we don't have to continue our calculations any further. So this is a rather complicated process, and we're going to spend today and our class meeting on Friday going through it. My hope is that we'll get through the first of the examples today, and then the other one we'll do on Friday. So here is that example. Remember, this is something that we wouldn't be able to do with the direct step method, because the direct step method would have no way to handle the fact that the channel geometry is changing. In this case, our section where we know the depth is here at location 1, where we know the depth is 5 feet, and this is a trapezoidal channel. The bottom width is 25 feet. You can see it's got a side slope of 2 units of horizontal to 1 unit of vertical. So if it's 5 feet deep, then that tells us we have an added 10 feet on the left side, 10 feet over here. And so capital B in this case would be 25 plus 10 on the left and 10 on the right. So we're going to try and find out what would be the depth of the water in a rectangular section that is 1,000 feet upstream? So what we're assuming is that it's gradually making the change, that these side slopes are gradually tapering upward through the 1,000 foot transition. And so we'll use a coefficient of expansion slash contraction of 0.3 because of that change in the shape. We're going to put 1,000 CFS through the channel. And bear in mind that when we have traditional units for Manning's equation, there's that coefficient in front of it, 1.49, that we ordinarily don't use for Manning's equation. And then the roughness of the material, whatever this channel is made of, has a roughness of 0.05. Okay, so let's open up the template file that I shared with you earlier today. Here it is. All right, so we can see, you kind of just have to mentally consider section 1 is downstream, section 2 is upstream. And so look at the invert elevations. That's another way to know which is upstream and which is downstream, is the invert is 5 feet, meaning that it's 5 feet from the bottom of our datum up to the bottom of the channel. But it's 7 feet from our vertical elevation datum up to the bottom of the channel at section 2. So section 2 is further upstream. The water is going from 2 towards 1 here. Now these are the formulas that we're going to use as we go through this process. And let's also put in some of the known parameters. So for instance, our flow rate in this problem is given as 1,000 CFS. Okay, so we'll put in 1,000 there. Our N value, the Manning's roughness of the channel, is 0.05. Z1 is the elevation above the datum at the channel bottom. So it's 5 feet at the downstream section and 7 feet at the upstream section. And then our coefficient of expansion and contraction is described as 0.3. And then we have a 1,000 foot section length that connects the two. Okay. So here at the known section, the geometry is given, and it's not going to change. So, for example, we know that the depth is 5 feet. They tell us that. So it's 5 feet in depth. So now we're going to try and calculate all of the parameters that we know about that shape based on its known geometry. So, for example, let me just paste in, I'm surprised it's not already on here. We've got that, the parameters, I think I'll get it from here. I'm going to paste the formulas that we know for trapezoidal geometry. So, all right, so over here, for example, we want the area. We're just going to have, for the trapezoidal geometry, b plus ty times y. And our t, let me define that up here. T, the side slope, is 2. Okay, and the reason why we say that is it defines 1 as the vertical and t is the horizontal component. So t is 2 based on the side slopes that we're given. So the cross-sectional area is the bottom width of 25 feet. So I guess I'll just type that in manually. 25 feet times the depth b plus ty times y. So b plus ty times y. All right, 175 square feet. And we're going to have several different iterations, but nothing is going to change when we, oh, I've got a mistake there because I didn't anchor the reference up to t. Nothing will change in our iterations for the known section, just the section that's upstream. Okay, so the velocity then obviously is going to be the flow rate divided by the area. So if Q equals VA, then V equals Q divided by A. So we've got the velocity at this, again, I need to anchor the reference up to the flow rate. All right, wetted perimeter. Let's go over here. I'll drag that over so I can keep it in view as I type it in. Wetted perimeter requires me to calculate the parameter W. So let's do that. W is 1 plus t squared to the power of 0.5. 2.23. All right, so now wetted perimeter is B, which is 25 feet, plus 2 times y times w. Anchor that reference up top, and we got the wetted perimeter. Hydraulic radius is defined as the area divided by the wetted perimeter, so area divided by wetted perimeter. So the hydraulic radius will be the same for each one of these different rows. Let me just drag this out of the way. Okay, so energy is going to be the depth as well as the velocity head, and we're also going to add in the delta z. Okay, so here E1 is Z1, anchor that reference, plus the depth, plus the velocity head. So velocity head is V squared divided by 2g. And here is traditional units, so we have to be careful that we put g as 32.2 feet per second squared. Okay, so that is the energy that we have, and that's not specific energy, that's total energy because we've added in the z component as well. So it goes back to this indication where we're adding up all of the energy at 1 and at 2 and comparing it. Okay, now slope of the energy grade line is going to be based here on Manning's equation, so that would be the slope of the energy grade line just at location 1. Okay, so it is going to be the n value, 0.05, times the flow rate, 1,000 CFS, divided by 1.49, that's the prefix that we use if we have traditional units. In fact, it's 1.486, but we'll just use 1.49. Multiplied by the area times the hydraulic radius to the power of 2/3, which is 0.66667. Okay, and then all of that is to the power of 2. So this gives us the slope of the energy grade line is 0.00644. Okay, now this is where things get interesting, where we have to assume some depth at location 2. And just as a starting point, let's say maybe it is a little bit deeper. All right, so I'm going to say 5.1 as my guess for the initial depth, So now if that is the depth, then the water surface at that location is the delta Z plus the depth. So it is Z2, anchoring that, plus the depth. So that's the elevation of the water surface. So from the datum up to where the water is. The cross-sectional area, since it's just a rectangular channel at section 2, that's relatively easy. We can just say it is the 25 meters wide multiplied by the depth. So that's our area. The velocity will be Q divided by the area. Okay, so it's this flow rate anchoring the reference divided by the area. I think it might be helpful if I add another column in here for the velocity head. And so I'm going to do that. It's not on your template file, but let's add an extra column in here. So right click at the top, insert, and then this would be v squared divided by 2g. It's going to have units of feet. So essentially, rather than calculating the velocity head somewhere separately, let's just calculate a column that gives us the velocity head. So if our velocity is 7.84, then the velocity head would be v squared divided by 2 times g, which is 32.2. Okay, so we've got that velocity head, and we don't have to have it. We could embed that in part of our formula elsewhere, but I think it may simplify things if we do have the velocity head on the screen. Wetted perimeter for a rectangular channel is just going to be the bottom width plus 2 times the depth. So it'll be the sides and the bottom. So 2 times the depth plus the 25 meter width across the bottom. So that's our wetted perimeter. And hydraulic radius by definition is the area divided by the wetted perimeter. And now E2 is going to be the water surface plus the velocity head. So E2 is going to be the water surface plus the velocity head. That's how much energy there is at location 2. So water surface plus velocity head. Okay, and we've got E2. And then we're going to use, once again, Manning's equation to say what would be the slope of the energy grade line if this is the depth. So if the water is that deep, then we could use Manning's equation to say what's the slope of the energy grade line just at that location where it's that particular depth. So again, we'll type in Manning's equation using the reference up here to the n value times the flow rate divided by 1.49 times the area times the hydraulic radius to the power of 2/3. And then all of that is squared. Okay. So that gives us the slope of the energy grade line. Yep, that's right. All right, so the observed head loss, remember, is just simply the difference between the depth, the energy at the upstream location and the energy at the downstream location. So the observed head loss is just E2 minus E1. So we've got 2.548 meters of observed head loss. Now SF bar is saying what's the slope of the energy grade line at the midpoint. So we need to add together the slope of the energy grade line at 1, the slope of the energy grade line at 2, and divide it by 2. So that gives us the slope of the energy grade line at the midpoint. And now the calculated head loss is going to be based on this formula. So it's the slope of the energy grade line at the midpoint multiplied by the distance between the 2 points. And so L here is defined as 1,000 feet. So that's how far upstream it is to section 2. Plus the difference in the velocity heads. And I guess this is where I'm going to have to bail out on this equation, because we have the velocity head for location 2, but we don't have a separate column that gives us the velocity head at location 1. Let's do that, because it'll make things quite a lot simpler if we have it. So right click here and let's insert a new column where we're going to have v squared divided by 2g. So this is going to be the velocity head at section 1. So it is the velocity at 1 squared divided by 2g. Alright. I'll change my template file for future semesters, because I think having that velocity head, as you'll see, will allow us to be a little bit simpler when we apply this head loss formula. Alright, so that head loss formula again was the slope of the energy grade line at the midpoint multiplied by the segment length, which is 1,000 feet, and now we're going to add the c value multiplied by the absolute value of the difference in velocity heads. Okay, so first things first, we'll reference the c value and anchor that and multiply that by the absolute value of v2 minus v1. Velocity head at 2, so it's this velocity head minus the velocity head at 1, which we just barely calculated. Alright. So what this is saying is, it's saying if you had the depth being 5.1, then that would mean that there's a calculated head loss based on what's happening with the slope of the energy grade line of 9.5 feet. And that doesn't match up with our observed head loss, which isn't looking at the slope of the energy grade line. It's looking specifically at just what's implied by the depth and the velocity head. So it's looking at the energy situation two different ways. This is looking, this column S for the observed head loss is looking at how much energy there must be based on the velocity head and the depth, and then the calculated head loss is looking at the slope of the energy grade line that we know applies when it's Manning's equation. So this calculated water surface, this is the formula we're going to use for the calculated water surface at 2. It's going to be the water surface at 1. Okay, so the water surface at 1. We don't have a special column for water surface at 1, but it is the depth plus the z. And so water surface 1 is the depth plus 5 meters, because that's z1. Water surface at 1 plus the velocity head at 1. Okay, so we'll click on, here's our v1, plus the head loss calculated minus the velocity head at 2. Here's that reference to the velocity head at 2. So it's telling us, I may have typed something in wrong here. Let's see. Water surface at 1 plus the velocity head at 1 plus the head loss calculated minus the velocity head. I think that must be right. All right, so plus 5. Yeah, so the water surface at 1 plus the just to be sure, I am going to create a column that gives us the water surface. So let me insert this where we've got the water surface at 1. And that's going to have units of feet. And this will be the last thing. We'll pause our, since it's already 149, we're going to have to pause after calculating the water surface at 1. But it is the depth plus the elevation at location 1, and anchor the reference up to that. Alright, so this is where we're going to pick up when we resume on Friday. We'll start with the calculated water surface at 2, and then we'll go through the process of updating and iterating and finding out how do we balance so that we have agreement between the observed and the calculated head loss. All right, it's 1:50. That is all the time we have for today. Remember that the announcements are the homework 12. You've got until 11:59 to solve that, and then the final exam will be the following Friday. All right, see you next time, everybody. Have a good day.